Okay, number 2a, the question says f at x is equal to negative 2, bracket x minus 3, and bracket squared minus 4. And Alright, so this is a quadratic function, so we know it's going to be something like this or something like this, facing upwards or downwards. And what's important here is this is the value of a. Do you use h and k for those two? Yeah? Okay. H deals with the x-axis, and k deals with the y-axis of the vertex, right? So if we were going to plot this, this is called vertex form. So it's in vertex form. So this is our x value. The only difference is if it says negative 3, we go positive 3. So we know we go 3 to the right from the origin. We always start from the origin. And then it says go down 4 from there. So we go 1, 2, 3, 4. So we're at negative 3, negative 4. Or in other words, sorry, 3 and negative 4. That's our vertex. So the 3 is opposite, and the negative 4 is the same. Does that make sense so far?
Yeah.
Okay. The question says to find number of zeros. Really, you only need the k and the a for that. The a is going to be stretching this parabola. But what's more important, it doesn't really matter how far it's stretched because it's either going to cross the x-axis or it's not going to cross it. And because this is negative, that means it's going to head downwards. So technically this is a parabola that's probably pretty thin. It looks something like this, not drawn perfectly. But because it's negative, it's heading downwards, okay? And because it's heading downwards, there are no x-intercepts. So in this question, the number of x-intercepts would just be there are 0 x-intercepts. But what's important now, say they ask us to state the domain and range, okay? So domain deals with our x-axis, okay, and range deals with the y-axis. So if we have our domain, we could say our domain is equal to, or we could put colons. Because this is a function, so a continuous line represents it, we're always going to start off with x is a set of all real numbers, okay? And then this straight line is our such that it states a restriction, okay? But in this case, this is a parabola, so parabolas don't actually have restrictions on the x-axis, okay? Unless they state it in the question, unless they say draw this between negative 2 and positive 2, something like that, there are no restrictions on the x-axis. So actually, I don't need to put this line here. I can just end that statement. The domain is x is a set of all real numbers. Okay, so that means essentially that this will continuously go this way and this way forever. Okay, we're going to start our range, the same idea. Range is equal to, okay, range is y is a set of all real numbers. But with a parabola, there will be a restriction on y. The restriction on y is that this parabola will touch every point of the y-axis as long as it's below negative 4. If I'm at negative 3 and I draw a straight line, I'm not going to touch the parabola. Or if I'm at positive 3, I'm not going to touch it. So anything below negative 4, that's where this parabola exists. So y is element of all real numbers such that y is less than and equal to negative 4. That would be considered our parameter. So we just use the variable, then we use a less than equal to sign, because we know it's equal to it because that's where it touches. It's tangent to this point. Okay, negative 4, that's our value of our vertex. Okay, say we have a different function like this. Okay, f of x is equal to the root of x of x. Okay, one way we can draw these is we'll just do a little. Okay, so we say we have our xy chart, or in this case it'd be an f at x. Sorry, not xy, but it would be an x because we have our variable x and f at x. Okay, so say we're at. I'm just going to take random examples for this one, okay? Because we're going to try to discover what a square root, what that function is supposed to look like. I'm going to take 0. 0 is an interesting one, okay? So I'm going to put 0 in. And let's say I had to put 0 in that function. We'll do it in red, okay? So they're saying f at x, or we replace x with 0, is equal to the root of 0. What is the root of 0? Do you know?
0.
Just 0. Because 0 times 0 will be 0, right? So our f at x is 0 in that case. Okay, that's easy. What if x is 1? Okay, same function. So f at 1 is equal to the root of 1. What's the square root of 1?
Okay.
Close. Square root is what times what equals that number. So what times itself equals 1?
1.
1, yeah, real simple. But there's a little trick here in the square root. I know this answer is going to be positive 1, but it's also going to be negative 1. So it's plus or minus 1. And the reason for that is if I multiply positive 1 times positive 1, I'm going to get 1. And if I multiply negative 1 times negative 1, I'm going to get positive 1 again. Okay? So I actually have two f at x's. This is how they write it. They write plus or minus 1. Okay? Another idea, I won't use 2 because it's going to be a decimal number. I'm just going to jump ahead to the next rooted number. So say we had 4. What would, if x is 4, what is the square root of 4 going to be?
2.
Yeah, but it's going to be plus or minus 2. Okay? So it's going to be both of those. So let's start to draw this. So when x is 0, okay, let's just assume this is on a scale of 1, okay?
Mm-hmm.
When x is 0, f at x is 0. So that means I have a point right here, okay? When x is 1, so I go over to x is 1, I have a point at positive and negative 1. So I have 1 point here at positive 1, and I have 1 point down here at negative 1, okay? When x is 4, I'll jump up to 4. 1, 2, 3, 4. I have a point at positive 2 and a point at negative 2. And the next easy one to work with would be 9. 9 would give me positive 3, so let's go 4, 6, 7. Here's 9. I'd have a point at positive 3 and negative 3. So, if I look at this, here's all my points. What if I have, I've plotted what I have so far. What if I had negative 1? What would f at negative 1, so the square root of negative 1, what would that be?
Is there minus 1?
If negative 1, what's a trick about negatives is there's actually no square roots of any negative number. Because you can't multiply a number by itself to get a negative number. You always have to do one positive, one negative to do it, right? So in terms of square root, they don't exist. So this is non-existent, okay? So that's going to help when it comes to our domain and range. It's going to help us make sense of things, okay? So essentially what they're saying is after the 0 to the left of it, this function doesn't exist, okay? So essentially, this is essentially what I have. And if you take a look, it looks like a parabola. The only difference is that it's sideways, okay? So let's talk about the domain and range of this one. In this case, what'll be easier to deal with first is I'm going to deal with the range first, okay? So our range is y, always deals with y. Y is the element of all real numbers. Is there a restriction on y? No, this sideways parabola that we have is just going to continue to go. It'll constantly go up forever, and it'll continually going forever and ever. So essentially, it'll go this way and this way forever. Nothing's stopping it. Okay. So there's no restriction on y. So we can just end it right there. Y is the element of all real numbers. But our domain. Again, we start with x is the element of all real numbers, but there's a restriction on our x. Can you tell me what the restriction on x is?
X cannot equal a negative number.
Can't be a negative. So in other words, x is greater than and equal to 0. Okay? So that's our restriction. This function only exists to the right of here. Okay? That's the only place. Anything over here, this function doesn't exist. Okay? So that's what our restriction means for that function there. Okay, so question 3 deals with these values of g, and what it is just 4 different points. So our first point is 1 and 2. So we go over 1, up 2. There's one of the points. Next point is 2 and 5. Next one is 3 and 7. 3, 7. And the next one is 4 and 8. So if you look at this, this is a bit of a curving line. Okay? Oh, sorry. This isn't a line, technically. I'll make that distinction here. Because they gave us specific points, it's actually just 4 points. So the 4 points, 1 and 2, I'll redraw them again. 2 and 5, 3 and 7, and 4 and 8. So these are your functions. It's just 4 different points. There's nothing in between. This only exists at these points here. Now, 3a has asked you to take y is equal to 2 times g at x. Okay? So what they want you to do is essentially whatever your answers are to g at x, okay, they want you plug in the value of whatever your x is for the g, and then you're going to multiply it by 2. That's what this 2 is standing for here. So in our first function, our y value is equal to 2 times g at x. Okay, so in our first example, and what's going to happen is in our 3a's, we're going to end up with another g, okay, and it's going to have 4 coordinates, just like the one above does. Right, we're going to have x, y values, so put our commas in. The only difference here is I'm plugging them in. So in our very first one, g at x, when I plug, when x is 1, I plug it in. So y is equal to 2 g at x when x is 1. So I'm referring to this one here. When x is 1, I plugged 1 in. Okay? What this has told us is g is equal to when x is a value. Okay? So when x is 1, our g value or our y value is technically 2. So this gets a little confusing, but what they're trying to say is this now is going to become the number 2, and we're going to multiply it by 2. So our new y value, I'll write this all in, okay, y will equal, we keep the 2 from before, and when g is 1, this is our 1, sorry, when x is 1, g is equal to 2, so we put that number 2 in, y is equal to 2 times 2, which means y is equal to 4. So our first coordinate, when x is 1, y is 4. So essentially this 2 is going to stretch everything. All we're really doing is multiplying the y values by 2, by plugging it in. So the next idea would be if I plug the number 2 in. Well, I know that when x is 2, g at 2 is 5, right? Because that's what this is here, our number 5. I do 5 times 2 is 10. Same idea with 3. I just end up multiplying 7 times 2 is 14. And same with 8, 16. So our new function, we'll do it in blue. When x is 1, y is 4. When x is 2, y is 10. And obviously this isn't going to fit, right? But these are our new points. And essentially what they want you to see is that this has been stretched by a factor of 2. Now they're using pretty tough numbers to work with right now, but that's the idea behind this, that we've stretched everything by a factor of 2. That's what this number, when it's outside the x value, it's going to stretch everything. They're trying to get you to recognize that idea because you're about to work with quadratics and transforming them. Okay? Let's do B so you can get an idea of what I'm talking about. That'll make a little more sense here. Okay, same idea. We have the same number 3. We're going to do 3b instead, okay? So g is still equal to the numbers above. G is equal to 1 and 2, 2 and 5, 3 and 7, right? And 4 and 8. So, same idea here, okay? The only difference is the new function is y is equal to g at x plus 2. So essentially, we're plugging in all these values for g at x. So let's try to think through this. The very first one we plug in is this example, okay? X is 1. So when I plug 1 into here, g at x is actually equal to 2. It's the y value. That's what they're trying to get at. It's the y value here, okay? So when this is our 2 function. So like I said, the same idea here. When x is 1, g at x is going to be 2. Okay? So I'm going to write that in here, right? So we'll do the very first one. Y is equal to, when x is 1 plus 2. We know that g at 1 is going to be 2. That's our number there. So y equals 2 plus 2. Our new y value is going to be 4. Okay? So when we're drawing our new y value, I know I drew it under here last time. I'm just going to erase this and put it below on this side. We're dealing with y equals g at x plus 2, right?
Mm.
Our new g, okay, our very first function is 1 and 4, which was the same as before, but you're going to notice the next one's a little different. In the next one, we're dealing with when x is 2, so g at 2 plus 2. Well, g at 2, when g's at 2, our y value is 5. So we plug the number 5 in for g at 2. So now we have 5 plus 2. So our new y value is 7. Okay? So essentially we have 2 and 7. Okay? And if you notice what's happened is all that's going on right now is we're shifting the y value up 2 spots. So this has gone up to 4, this has gone up to 7. What's our next y value going to be? Yeah, that's it. If we go to plug this all in, our next y value is going to be 9. And what will the last y value be? We're only shifting by 2.
2. Oh. So
8 plus 2 is
10.
long day, right?
Oh.
That's okay. So, what they want you to see here is that, again, I'm going to graph the original. There's 1 point, 2nd point, 3rd point, 4th point. What they want you to see now is with this, when it's outside over here, this went up 2, this went up 2, this went up 2, and this went up 2. So this whole function shifted upwards 2. Okay, that's the idea of, that's supposed to be a k, the letter k. If you notice in this is supposed to represent k. Remember we were just talking about that? In this one, this was supposed to be a. A stretches functions, k shifts them up and down on the y-axis. In this one, do you know what would happen here?
You will move to the left too.
Yeah, you'd move to the left too, and that's what they want you to figure out here. And this one, it reverts the stretch. This one gets horizontally stretched. And it ends up being by a factor of 2, or is it in half? Well, either way, it's a horizontal stretch rather than a vertical stretch. The first one deals with a vertical stretch. This one deals with a horizontal stretch. So that's what they're trying to get at there. Right now, though, they're only using 1 point at a time. You're going to start doing it in quadratic functions. When it's in a quadratic function, it's a little easier to see because the entire shape is moved and stretched and shifted. It's usually with those it makes a little more sense. Okay, we're going to make an XY chart of this, or f at x, okay? So my graph goes from -10 to +10. So I'm just going to insert those values. I'm going to go from -10 all the way down, okay? 12, 6, 5, 4, 3, 2, 1, and then we go 0, 1, 2. So I'm using all the numbers on my graph because I want to plot all the points right now. We'll continue the other one after. What's going to happen here is my very first example, I'm going to plug -10 in for x. So in our first example, we have f at x is equal to, oh sorry, not f at x, but f at -10, because I'm replacing x with -10. F at -10 is equal to 1 over -10. That's it. So my f at x is 1 over -10. Now what's going to happen when I plug in -9? What will my f at x equal? 1 over -9. So the pattern is going to be 8, 1 over -7. Sorry, there you go. 1 over -6. 1 over -5. Oh, it'd be nice if I write it like this. Does this make sense to you?
Yeah.
Okay. 1 over -2. -1 over 1. Now this one is when x is 0, 1 over 0. So this is 1 over 0, and this one's 1 over 1, 1 over 2, and then obviously it's going to be 1 over 3, 4, 5, 6, 7. Apparently I only made it go to 8, or to 9, sorry. Okay, but the whole point of this, okay, so when I go to plot these, you're going to see what happens here. When x is -10 and I'm down here, my y value is -1/10. Well, -1/10 is like just here. Okay? It's almost on the line, it's not. When I'm at -9, I'm at negative 1/9. So it's a little lower. Okay? A little lower. And it keeps doing that pattern. It gets a little lower. Da-na, da-na, da-na. Then we get to negative 2. Negative 2 is at negative 1/2. So here's a key one. So at negative 2, I'm at negative 1/2. So I'm halfway down that point. Negative 1, I'm at negative 1. So I'm here. Now what's important here is at our 0, sorry, this isn't 1 divided by 0. Have you ever tried putting 1 divided by 0 in your calculator? It's an error. And what it means is it doesn't exist. If you put it in your calculator, you get error. Okay? So what it's saying is it doesn't exist. So we have something that's coming across here, starts coming down, and what actually happens is it goes like this. And it gets closer and closer and closer to that line, but it never actually touches 0. The idea is like walking halfway to a wall. Anyone ever told you that? To walk halfway to a wall? If you walk halfway to a wall and you continue to walk halfway, you'll never get to the wall. Does that idea make sense to you?
Yeah.
So this is constantly getting closer and closer and closer to the line, but it's never actually getting there. It'll never touch the line. So what ends up happening now is after 0, this function comes down from here. At 1, it's at 1, and then it's negative 1/2 down. Obviously, I didn't draw it great. But here's the idea of this function, okay? There are 2 lines. It's called a reciprocal. Essentially what they're saying is if I were to draw like a line this way across, yeah, it'd be a mirror image of the other one. I don't know why this is. There you go, got it. Okay, so if we were to draw a line like that, it'd be a mirror image. So, this thing's going very slow. Okay, so it'd be a mirror image of this. Obviously, that line's not drawn well. Sorry that it's still moving. It's just so, when you write the domain and range of this is where it's going to get a little tricky. Okay. Our domain and our range are going to be very similar. Okay, our domain is X is a set of all real numbers such that there's one restriction. It doesn't exist at one point. What point doesn't it exist at? At 0. It doesn't exist here. So, such that X cannot equal 0. Okay? That means it doesn't exist there. And the same idea is with the range. Y is a set of all real numbers such that Y cannot equal 0. If you notice, it never touches the y-axis and it never touches the x-axis. Okay, so that's what they're referring to when you go to write the domain or range of a number like that. So if we needed to shift it though, all you'd have to do is in this question, you see how it's x minus 2? You plug in values of x and you plot them, and you're going to see how it's going to shift the entire reciprocal. What will end up happening is you'll get a reciprocal maybe, excuse me, this one says negative 2, right? So when x is 2, so you're going to get a reciprocal like this. So you're going to get something like this. It goes like this, and then you get a number like this. So if you notice, down the number 2, that's when it's not going to exist. Okay? So this function won't exist at 2 in your first A. And what you're going to do is I want you to try to plug the numbers into A, and you're going to see how that works. That they won't. Okay. What's important to realize here is P and Q deal with transformations. So that's moving the function. P deals with x-axis movements. So that's moving the function. Let's say it was a function like this. P deals with moving it to the right or moving it to the left. Okay. Q deals with y-axis transformations. So say we have the same function, something like that. Okay. Q moves it up or moves it downwards. Okay. So we have that function. Now, so P and Q are transformations of it. A and B deal with stretches. A deals with vertical stretches. So say this was our original function again. A vertical stretch would be something like this. Go up like that, and then maybe we come down like this, and up like this, down like this. See how it's been stretched? It's still meeting the same x-axis points. So it's been stretched upwards and downwards. That's what A deals with. Okay? And B deals with horizontal movement. So if this was our original again, say we have something like this. B deals with stretching it like this. So you see how it's been pulled out wider like an accordion? That's the idea. So the tops and the bottom should still stay the same on those. I drew it a little off. But that's what the idea is. B deals with stretches left and right. And the reason they put this letter F in here is because we don't know what the function is. For instance, a function could start off, there's many different ones. For instance, f at x is equal to x squared. This is a quadratic function. Or f at x, remember we just did this, square root of x. Okay? This would be, what's the name for it? It's a root function. It's essentially a sideways parabola. A reciprocal function, that's what our f is. In this one, this is a linear function. It's just a straight line. So what they're saying is this function, see how it's squared, it's a square root, it's a division by 1, it's nothing essentially in this one. That can always change, but the numbers for a, b, p, and q are always going to affect the function the same. Okay? So for instance, I'll show you an example of this one here. This one here, f at x is equal to, and we'll underline them after. Let's say we have 5. Oh, well, this is a quadratic function. So in a quadratic function, we actually don't get a b. Let's say it's like this. Minus 3 squared. Oh, I see. Plus 4. Those are vertical stretches. And another way we can affect this. Okay, so sorry, here we go. So essentially, here's our a value, our b value. It's attached to the x. It's been multiplied by the x. Okay, this is our p value and our q value. Okay, so that's how these numbers are going to affect. This is going to move it left and right. This is going to move it up and down. This is going to vertical stretch and horizontal stretch. Same idea happens in this function here. Okay, this function here, let's say we have f at x is equal to, we use the same numbers, okay? 5 root, and then we have 2x minus 3, and then this is plus 4 on the outside, okay? Same idea. Here's our a, our b, our p, and our q. Okay, horizontal stretch, horizontal translation, vertical translation. Okay, reciprocal function. At x, we're going to have a reciprocal function. Technically, actually, let's write it like this, just so you can see it. 5 times 1 over, and then you got like 2 x minus 3 plus 4. So can you see that a little bit? Yeah. So here's our a, b, p, and q. Okay? This function's been changed a little. Okay. Now, the only difference here is in this one, because the 2 is already applied to the x, I instantly know this is going to be a shift right and left 3. On this one, I haven't distributed the 2 yet. So technically that 2 is going to change this 3. So it's going to be like a 6, okay? And same with this idea here. Technically the 2 has to be distributed, so that's going to be a 6 also. Okay? That's the idea there. But these are ways they could use to stretch it up and down, move it left and right. Let me quickly think of a linear function. I haven't done this with a linear function. Okay, so let's say we have our quadratic function. We know that this is going to deal with transformations on the x-axis and the y-axis, and it's just moving the vertex, okay? So negative 3 means I'm going to the right 3, and positive 4 means I'm going up 4. So here's my new vertex. Now, there's a stretch on the horizontal, and there's a stretch on the vertical. So if we're stretching, let's do one at a time, okay? One at a time. Let's say I was just doing this stretch here. This stretch here means if I go over 1, okay? So if I go, and I always start at the vertex. Have you ever drawn a parabola before?
Yeah.
Sorry. So normally when you draw a parabola, the rule is you go over 1 and you square it, okay? Yeah. Then you go over 2 and square it. So I go 1, 2, 3, 4, okay? Back to 4. Same idea. So you get something that looks like this. We'll call this our original, okay? That's if A is 1. In this case, A is 5. So what happens is I go over 1, I square that number, I normally go up by 1, then I multiply whatever I'm going up by my new A, which is 5. So I go over 1, now technically 1 squared is 1, 1 times 5 is 5, so I go up 5. So here's my new proof, my 2 new points. So if you look, and obviously if I do the next one, it's going to be way off the screen. I know it's not perfectly flush, but it's much thinner. If you look at this parabola, it's much thinner than it was before. Now, a vertical stretch, or sorry, a horizontal stretch, let's move this. Put these, this is our original again. We're still at our vertex here. The vertical stretch is by a factor of 2. So normally we go over 1, up 1. Think of it the other way now. Instead of going over 1, up 1, I'm stretching it by 2. So when I normally go over 1, I multiply that by 2. And I'm going to go up the same amount as before. So I go over 1, 2, up 1. 1, 2, up 1. Okay? So already it's a wider, here was an original point. Normally my next step is to go over 2, up 4. Well, instead of going over 2, I go over 4. 1, 2, 3, 4, up 4. So you notice this is a horizontal stretch. This has been stretched sideways. Does this make sense? They've pulled it out. It's like a fatter parabola. So that would be dealing with a B. This would be dealing with an A. Okay?